Okay. Oh. All right. If we want to find the acceleration vector, come on, pen, work for me. I just started recording. There we go. We want to find the acceleration vector at a particular time, and we are allowed a calculator. That means don't differentiate by hand. Let the calculator do it for you. However, you can have fun and differentiate by hand, but if this was a test problem, you would definitely want to get your calculator out. You are given dx dt, which is the x component of velocity, and dy dt, the y component of velocity. That means the velocity vector are these two functions in this order. To find the acceleration vector, I need to take the derivative with respect to time of dx dt and the derivative with respect to time of dy dt. And that will give me the acceleration vector. But I only need to know at one particular time what my acceleration is. That means that I'm going to tell my calculator that it needs to take the derivative of that highlighted function at 2. What you can do is in your calculator, go back to regular function mode. And you can put this function into your y1. And by the way, if there are many ways to do this with your calculator, this is just giving you a way if you don't remember how. When you plug this into your y1 in function mode, you need to use the x variable button. And then if you push second and F4, push second and the F4 button, one of the things down that menu is dy dx. After you push enter on dy dx, you're just going to push 2. Enter. And it will tell you the slope. That is your x component of acceleration. Then do the same thing again, but for the second function. And you should be getting, let me find it. I have way too many things up right now. This one. Okay. Did I not write the actual numbers down? No, I did not. Can someone tell me what they got for their acceleration vector in letter A? Let me see. And I just need someone to agree that that's what they got, and I feel confident. 1.746. And excellent. 3.027. So that's part A and how to use your calculator to do it. Part B wants you to write an equation of a tangent line at t equals 2, but be careful of the wording. And this problem was actually created after AP problems like it were made. It wants equation of the tangent line to the curve. Realize what you are given. You are given the velocity vector. not the position vector. The position vector is the curve itself. You only have the rates of change to the curve. One of the biggest issues with the AP test is taking a moment to identify which functions they actually gave you and just realize what they gave you. That alone is half of the problem, half the battle. With a tangent line, you're doing y minus y coordinate equals slope times x minus the x coordinate. But be careful, because this is how it's a little bit different when you're dealing with vector or parametric curves. You're used to putting in this spot the input variable. But the input variable now is t, not x. You need to have the x coordinate at t equals 2 plugged into that spot, and the y coordinate at t equals 2 plugged into that spot. And lucky you, they told you. Yay! Then slope, you know that slope is dy over dx. But do you see a little bit of algebra move to make this something you already have? If I divide numerator and denominator by dt, conveniently, you already have dy dt and dx dt. You just need to find it when t is 2. So I'm going to put a find this, and I'm going to put a line way down here to say plug in t equals 2. Oops, hold on, I'm messing up where I'm looking. So the position is y coordinate 4, x coordinate 1 is given right here. And then can someone tell me what they got for the number of slope? Put it in your calculator. It gives you a nice little decimal number. What is that decimal number? Know that the AP test allows you to truncate or round up. So as long as the fourth, was it negative 0.660 and then a number bigger than 5? Okay, both of those are correct then. Thank you. I'll just do the rounded up version here. Negative 0.661. And once you have an equation of a tangent line, if you are in a free response test, leave your answer that way unless it specifically asks you to isolate why you don't need to. Now, do you remember what the formula is for speed? For some of you, you can remember that speed is the length or the magnitude of your velocity vector. And that's enough said, and you know what to do. The formula for speed is Pythagorean theorem on the rate of change of x with respect to time and the rate of change of y with respect to time squared. We're looking for the speed at time t equals 2. So you are going to plug 2 into the t's of your dx dt and your dy dt, and then let a calculator finish that up. I'm just going to write this in to make sure everyone sees. Okay. Once you get that number, somebody tell me what you got for speed. What is the decimal number? 2.473. And do I have an agree? Did other people get that same result? Or are you, oh, okay. Let's double check. Make sure you find square and then add, then do the square root. Okay. So it might have just been a silly error on the calculator, which unfortunately happens to us all, just hopefully not in the middle of a test. 186. All right, excellent. Then one thing left, finding the position of the particle at time t equals 1. Know that this is a very, very common question on the AP test, and not necessarily just pertaining to what am I trying to say? The vector motion, just asking you to find basically a solved number of a differential equation, knowing one number on that differential equation. Every time that happens, you're going to use the fundamental theorem of calculus. This one is a little bit trickier because you're given the position at time 2, and you need to find the position at time 1, so you're actually having to go backward. And actually, oh, I had the solutions right there and I forgot. Good job. So this is one way of looking at it. I have found that with some students, I need to just directly say how to use the fundamental theorem of calculus. If you take your dx dt function and you integrate that from some t equals, actually, let me go t equals alpha to t equals beta. The result of that is going to be the x position at time beta minus the x position at time alpha. Make sure you take a look at this. You know the fundamental theorem of calculus. You either understand it in this format, or you can start it in one particular memorized format and just use that. Your calculator will give you the definite integral number. So when you integrate from 1 to 2, the sine of t cubed, you are going to get the number, the answer to 1 minus that. can't think right now. I should say I can't arithmetic while I'm trying to do this. You know that x of, where is it? X of 2 is 1. So if you set up this equation in this way, you'll end up with the same answer in the end. I just know I need to point that out to you because some people depend on just using the fundamental theorem of calculus in its raw form every time. All right. Then hopefully you are good with your calculator and some of these formulas are making sense to you. Oh. So as far as the way this answer can be written, I've got to tell you that unfortunately, there are still some textbooks that will write vectors with round brackets. Unfortunately, people have preferences with notation. I prefer to stick to notation where you can tell one symbol from another symbol without having to read the context of the problem. When you use round brackets, that could mean an interval, it could mean a point, it could mean a vector, and I really try to avoid overusing those round brackets if I can avoid it. So I'll always write it that way, but know that it is actually okay to write it that way with the round brackets. Yes, question.
And then for the x of 1 and like the x of 2, would those be like bolded or have a little arrow?
Good question. No, because they are an individual function, where a vector is more like a group of functions. Mm-hmm. Okay. Now, right now I'm going to move forward onto the new formulas. I'm sending, I hate to say just we're learning more formulas, but yes, we are learning some more formulas. And I'll go over some more things. There's my reminder, record, I'm recording, okay. We did arc length already, but we did not do it with vector parametrics. So I'm going to go back and remind you real quick of what we saw and how it looked slightly differently, but yet how it's also the same. When we did arc length, we were looking at a singular function y with respect to the x variable. So we were stuck with a certain type of function when we learned that formula. Real quick to remind you of what we did there. If I want to find distance, I need to Pythagorean theorem my change in x and my change in y. Whatever variable you cut up into small pieces, that's the variable that you need to end up with respect to with your integral. That needs to be your differential. So I need to have a delta x as a differential if I am cutting x up into tiny pieces. So I divided by x squared and divided by delta x squared and multiplied by delta x squared, and that created this formula. Now, when I come over to our parametric friend. Now, time is what is being cut up into tiny pieces. So you have an X and a Y coordinate here at some initial time. At another time, you have an XY coordinate at point P1. The delta time is not visually seen in this graph like it was in the previous one. However, I get to go to the same essential formula of Pythagorean theorem, and my change in X is always, or my horizontal is change in X, my vertical is change in Y, which you might remember as like Y2 minus Y1, X2 minus X1 when you're looking at two particular points. And I want a formula for arc length. So I'll put, and actually your textbook uses the capital letter L here, so I'll go ahead and use the capital letter L for length. This formula is actually easier than the first one. We start off with Pythagorean theorem of leg squared plus leg squared equals hypotenuse squared. Whatever is being cut up into small pieces, that's what I need to, in this formula, divide and multiply in this manner, because that's going to allow the formula to show itself. Then when I take a look at what that actually is, I split the multiplication under the square root, and I get just a change in t out. And then I have change in x over change in t squared plus change in y over change in t squared. Ding! Now, does that formula actually look familiar from yesterday? That is the formula for distance traveled. So now I want you to take a moment to think about how distance traveled and arc length are one and the same if you are dealing with vectors or parametric equations. Oh, no, this one. The notes from yesterday, I want to refer you to right here, and let me emphasize highlight, and then I'm going to erase the highlight. I'm talking about these two right here. I'm going to erase the highlight. Okay. Where'd it go? Shoot. Okay. I have to wait. I'm having lag. See? I'm not responding to you. I love it when my computer says, not responding. I'm not responding. Oh, dear. Oh, good. Phew. Okay. When I'm dealing with parametric and vectors, arc length and distance traveled are the same thing because I actually get to see the literal path with a parametric or a vector valued function. But I want to make sure you're clear that the arc length formula for regular functions is not the same thing as distance traveled when we're looking at the linear motion. And that's because when we graph our linear motions, we use time as a physical dimension. And that means what you see if you are looking at a position function with respect to time, that is not the actual path traveled because you're only going back and forth on a line over time. So the formulas are very, very different, and I want to point that out and make that clear. So that's arc length. Then there's one other formula you need to be aware of. And I'm deciding that we probably don't need an example. It's just literally following a formula. And I'm going to move over to our next issue. When it comes to the formulas that you need for parametric and vectors on the BC calculus exam, this is the last formula you need. And then it's just a matter of playing with vector motion to make it have more sense. So here we go. We are starting off with a position function. And if I write it in parametric form, then all I do is I say, this is my x function with respect to time, and this is my y function with respect to time. If it were given to you in vector form, and I just am pointing this out, you don't need to write this down. Vector form doesn't say x equals y equals, it just lists the functions in an order, and you understand the first one is x and the second one is y. That's the only difference between parametric and vector from a mathematical point of view in the equations. It's just the way it's written. Now, slope. We just looked at slope when we did equation of a tangent line. Slope is always the change in y over the change in x, but you have the lucky issue of you have a function for x with respect to time and a separate function for g with respect to time. That allows you to make this little smooth move. And if you want to find slope, dy over dx, you are just taking the derivative of y and dividing it by the derivative of x. The dt's cancel each other out because you are dealing with a ratio of two derivatives. Now, I am going to call this slope a function, and I'm going to name it m because we're familiar with m representing slope. So this is slope with respect to time, and I want you to take a moment to understand. We started with an x and a y function. We had two separate functions with respect to time. With slope, I only have one function with respect to time, and that makes all the difference. So listen very, very carefully to what I'm going to talk you through so that you understand the formula that you must use for concavity. Whoop, don't want to show you the formula yet. I've got to add some space. Okay. So, concavity, first of all, if you want to know whether you have a concave up curve or a concave down curve, you need to know the second derivative of y with respect to x. Now, that means you need to from the dy dx that you got from slope, you need to differentiate with respect to the x variable to get the second derivative of y with respect to x. See, we got lucky with slope because when I had a ratio of two functions with respect to time, that little issue of you're taking the derivative with respect to x, but there's only t's there. We're able to just overwrite it super quick and not even maybe realize we're overwriting it. But you have to realize it when it comes to concavity. So what I'm going to do is I'm going to write this function in place of dy dx to make sure that this is clear. When I have it written this way, you can see a little bit more the fact that you have a function with a t variable and you need to take the derivative with respect to a different variable. So how do you do that? And remember, it's the chain rule. You can think of t as being its own little function with respect to x. And so you take the derivative of the outside mommy function, give mommy her baby, multiply by the derivative of the baby with respect to the variable that we are differentiating with respect to. Yep, that's exactly it. What you wrote in chat. But hold on. We're not done yet. Because you want to realize that in order to get to where we're at there, you already found dx dt. This is asking you for dt dx. Take a moment to think about it. Who wants to save time? Everybody wants to save time. So, well, what I'm going to do is I'm going to take this formula and I'm going to say, you know, how about instead of multiplying by dt dx, I divide by its reciprocal, dx dt. Those are some fancy moves, but will save you a lot of time. If you are stubborn and you want to find dt dx, you're going to have to go over to this function, isolate the t in terms of x, and then take the derivative of that with respect to the x variable when you could just use what you already have. And that's why the formula for concavity is the way that it is. And it will seem awkward to you. Why does x get all the attention and we ignore dy dt? You need to stop and just think about that with the formula. Every time you take a derivative, you have to be clear about what variable you are looking at the rate of change with respect to. That always affects the formula. Since I had to differentiate with respect to x, I had to deal with an extra dx dt. I didn't need to play around with dy dt. It wasn't with respect to. Now, the formula looks like this. and we need to practice. So this one I do want to do an example with. It's not just straightforward follow the formula. Although some of you are fine, I know that a lot of you need to see this and double check that what you're doing is correct. So here we go. You're going to find dy dx and then go and find the second derivative. So everybody's working on the problem. And hopefully you're doing the math. I'm looking to see, it looks like most of you are mathing. Some of you, I'm not entirely sure whether you're mathing or not. Yep, the thumbs up is exactly one of the places I'm looking. Are you mathing? Okay. The reason teachers want your webcams on is partly just so we know you're actually doing work. And until we get those touchscreen Chromebooks, I don't have a nice, necessarily easy path to check your screen. When those touchscreen Chromebooks come, I can look at what you have on your screen and thus actually know that you're working. Okay, here we go. Hopefully you are on top of this and you're ahead of me a little bit. To find dy dx, I just need to do dy dt over dx dt. Done. To find the second derivative for my concavity, I need to take the derivative with respect to x of that formula. But to save time, I'm going to take the derivative with respect to t of that formula and then divide that by whatever dx dt is, which I happen to have already found. And let me just give you a warning. Due to my own personal, when I tend to make silly errors, I would recommend that if you know this is where you are going, after you write equals, set a nice little division bar and put dx dt. Dx dt is 3t squared minus 12. Write that down now, because when you're done with the quotient rule, you might forget that there's a next thing to put in. I'm very good at forgetting there's a next thing to do. So I've learned to kind of keep myself from that by throwing in what I want to not forget as part of the formula first, and then dig in. To take the derivative, I'm using the quotient rule. Low d high minus high d low. Square the bottom and away we go. And while this isn't going to just happen every single time, it will happen every time you have a quotient and need the quotient rule for your slope. And that is, you could almost say cube the bottom and away we go instead of square the bottom and away we go. But I don't want to say that because that is not a rule. And so I'm going to distribute my 2 to give me 6t squared minus 24, and then multiply to get negative 12t squared. Ooh, we're almost all algebra simplified. Now, I will tell you I left out the next step because it's something you have done already. But the next step would be to determine what are the t intervals where you are concave up and concave down. And I'll go ahead and throw this out there real quick. This numerator is going to be negative no matter what t you plug in. This denominator is equal to 0 at plus or minus 2. This denominator would go plus minus plus, but because of the numerator, it's going to go minus plus minus. So that allows you to determine the time intervals where this graph is concave down and the time intervals where this graph is concave up. Okay. That finishes up all of those formulas. I'm going to stop recording.